Welcome to CPE 329, debug tools and miscellaneous stuff. Not really sure what to call some of these things, like talking about capacitors and wires and stuff like that. Okay, so debug tools are different methods of debugging your project. Some of them you've already done. Visual testing, for instance. There's also many chips, microcontrollers and microprocessors may have a software simulator. There's also in-circuit debuggers and in-circuit emulators, and I'll talk about the difference between those. Visual testing is what you've done in this class so far, so basically look at LEDs, press a button, see what happens, capture things on scopes, and in UART, if you've already done the UART tutorial, UART is actually a really handy debug interface. Software simulators are a computer program that mimics how the processor works, and usually they'll try to be cycle accurate simulators, and some have modest I/O capabilities, so you can maybe set a pin or clear a pin on some I/O interface, and it will, when you're actually walking through your code, you can actually do it. So you can actually try this in AVR Studio. You just go to the debug menu and hit Start. It'll bring up your code. You can set breakpoints, which is nice, so you can just run to and it'll stop when it hits the breakpoint. You can single step, meaning you can single step on each line of code. You can actually view the disassembly, the assembly code that is generated by the C compiler. And to do that, you go down to View Disassembly here. And it's kind of fun, but many chips have moved away from using software simulators because they're actually pretty tricky to make to match all the different types of hardware that a company makes. So instead, a lot of companies use in-circuit debuggers. Also, some people call it in-circuit serial programmers. And it uses some external hardware to talk to the microcontroller, and so it usually connects between 2 and 3 pins on the microcontroller. So you need to have 2 or 3 pins on the microcontroller dedicated for this type of thing. The in-circuit debugger also downloads usually a small amount of code to your processor, so you need to have a little bit of code space left. So for our 328P, you'd have to have about 5 KB of memory left over in the 32 KB of memory. But it allows you to do breakpoints, run, and step, and watch variables right on the chip, which is really nice because you'll have all your I/Os connected to that chip, and so you can allow you to test I/O routines, which is pretty handy. An in-circuit emulator is typically the most expensive debug tool that exists, and you use either JTAG or SWD interfaces. I'll talk about what those are. The biggest difference is it requires no software to be placed on the microcontroller, and it gives you access to the per cycle state of the microcontroller, whereas if you're using in-circuit the software debuggers, it'll stop as soon as it thinks it's capable of doing, essentially. So these are used more extensively for testing microcontrollers in the factory, but also for people who really need per cycle state information. And or don't have memory to put code on their chip just for debug. Okay, so JTAG is one interface for in-circuit emulators. It stands for Joint Test Action Group, which is a crappy name, but it stands for and it uses IEEE 1149.1 format. It's a specification that's done through the IEEE body. It's a serial boundary scan chain. Basically, many of them, if not all of the memory elements on the chip itself, like flip-flops, will have an input where you can shift a bit into it, and so all of these flip-flops and memory elements on this chip will be chained together, and you'll be able to shift a series of ones and zeros into the flip-flops to put the flip-flops in some known state. Because of that, there are often million devices in the chain, and so it could take quite a while to actually program via JTAG because it's a serial thing. So there's a test data in, test data out, test clock. This is how it's a serial connection, just similar to SPI. And then there's some control values like reset and mode select. The serial wire debug is a 2-pin interface, and it's becoming more popular than JTAG. And it actually takes a slightly different approach. It allows you to read and write AMBA bus transactions. So the AMBA bus is used by many system-on-chip vendors. It allows allows a company, let's say, who wants to, let's say, license an ARM core and then buy some intellectual property, let's say an MP3 decoder, and interface that to an ARM core. And that connection in between is usually nowadays an AMBA bus. It's I forget what AMBA stands for. It's some group that has a specification for the bus and how it looks. And so what this allows you to do is actually read and write the bus transactions, and then if you sequence them correctly, you can pretty much set up the state of the processor through using this type of tool. The biggest reason I think it's becoming more popular is the 2-pin interface, though. Okay, so on to other issues. Noise can be a big issue with microcontrollers. So there's current loops. If you have wires that are popping up like on our breadboards and stuff, you can have the area under the loop. It has an electric field, generating an electric field, and this can add a lot of noise. We can have capacitive coupling, so a trace on, let's say, a PCB next to another one. If one of them is bouncing up and down, the other one will be capacitively coupled to it and will also bounce up and down. Sometimes on PCB designs for high frequency signals, what they do is they run ground lines in between these lines. It takes up more board space, but can help with the capacitive coupling problem. If you have really high frequency circuits, you may want to put a Faraday cage, some sort of metal can around that circuit to really kind of capture any stray EMF. And so if you open up an old cell phone or something, you'll see around the RF circuit, there's usually a metal cage around there. Other things you could try if you have real big noise problems, you may want galvanic isolation, meaning that you have no common ground or power. And the way to do this is to use opto-isolators. Basically, it's a coupled photonic LED, or like an LED transmitter receiver pair, and you can communicate via photons across, so you have no common ground there. And then finally, one thing that a lot of people have to worry about is power supply noise, and we'll use decoupling capacitors, so I want to talk about that. So a decoupling capacitor, you can think of it as like a local storage for power, right, to kind of smooth out any variations in power. And so near the power supply source, you usually want a large capacitor to get rid of any low frequency noise. And so what I've read is between 20 and 100 microfarads of a capacitor, and we'll talk about electrolytic versus tantalum capacitors in the next slide. And then near the processor, we're worried about high frequency noise. The low frequency noise is gone, but on the board or near the chip itself, because there's a lot of digital circuits that are switching really high frequency, we'll need to use lots of small resist capacitors to filter out high frequency noise. And so it's oftentimes best to use some sort of blend of different values of capacitors here, but this takes up board space and cost. So lower cost boards will have not as much decoupling capacitors on them. And for this type of thing, surface mount is clearly preferred, because the leads of a through-hole capacitor actually introduce a lot of error. Okay, so ceramic capacitors look like this. They're typically small values and small in size, but we like them for high frequency noise. So put electrolytic capacitors. They're pretty cheap. They have a poor accuracy, and the worst part is they change over the lifetime of the capacitor. Usually cheap electronics have a lot of electrolytics on it. Tantalum is has about the same range of electrolytics, but better accuracy in lifetime, but also more expensive. And they kind of look like this usually. Okay, almost every processor uses a crystal. Actually, our ATmega 328P has a 1 megahertz internal RC oscillator that you could use if you didn't want to include an external part. They're usually made out of quartz, and they exhibit the piezoelectric effect, where if a voltage is generated with stress, or vice versa, its crystalline structure allows it to vibrate at a fixed frequency. So that's why we use quartz. It's a nice crystal. And a lot of people use the oscillator modules, which look like this. It's a 4-pin device, but it has like the capacitors here that are needed to kind of provide the little instability point across this crystal here. So all of these things are in this box here. And you can see this is a 1.8 megahertz, and this is a 32 megahertz oscillator module. Okay, so on to the next topic, wires. Wires aren't very sexy, but we can see here the gauge of wires. The very, very thin wires are like 40 gauge wires. Thicker gauge is 22. If you're into power distribution, you probably get into gauges of wires that I don't even think is appropriate for this class. But you can see as the gauge gets thicker here, the resistance goes down. If the wires get thinner, the resistance goes up. And this is ohms per 1,000 feet, so it's still only 1 ohm per foot here in 40 gauge wire. And there's different power ratings here. So just something to think about. Along with wires are connectors. Connectors are broken up into multiple different parts. A is the housing here. B is the conductor, the wires itself. C is the terminals and contacts. And D here is other features, like this is, I guess, a little locking feature that locks them together. So termination is actually, ideally, should have 0 resistance. And here we can see the wires inside here. The wire gets placed inside this little channel here, and you have a little crimping tool that crushes these crimp tabs into the conductor here. These here are holding onto the insulator here for more stability, and so not all that interesting, I guess, but just something to know. PCB connections, you can have through hole, you can have surface mount termination, things like that, and I believe that's the last slide. Yes, it is. So thank you for watching.